this video we look at the instantaneous rate of change. So in the previous video we looked at the average rate of change. Now we're going to look at the instantaneous rate of change. Just a reminder that the average rate of change really was asking, how do we find the rate of change between 2 points? So let's just choose 2 points on this graph here. Let's choose one down here, say the vertex, and another one up here, just to keep things nice and simple. If we want to find the average rate of change between those 2 points, we draw a nice straight line between the 2 points and we find the slope of the line that connects those 2 points, and that gives us the average rate of change. What we're going to look at today, though, is the instantaneous rate of change. So what that means is, instead of looking at the rate of change over a certain distance, we want to look at the rate of change at a specific point. So for example, we may try to find what is the rate of change right at this very instant right here. And that's why we call it the instantaneous rate of change. And you can see that creates a problem because we don't actually have a line at this point. Over here, when we were finding the average rate of change, we were able to draw a line. And then just a reminder, this line was called the secant. And we were able to find the slope of that secant, which gave us the average rate of change. So just a reminder about that. What we want to do now is kind of move away from finding the rate at between 2 points and try to find the rate at a given point. And as I said earlier, this doesn't look like there's a line here. However, we can draw a line on this graph that goes through that one particular point. So the idea here is that we want to draw a line. Maybe I'll get the line tool out. That might make this a little bit easier. Draw a line that just touches that one specific point. We'll see how we do here. Not very well so far. All right, there we go. So the idea is, I missed a little bit, but I'll just move it into place. That line is the line that we want to find the rate of change of. So let's see if I can just grab it here. Oh, I seem to be grabbing the graph. So the line that just touches that point, we call that line, it has a special name, we call that line the tangent. So just label that. So that line is called a tangent. And what we want to do when we find the instantaneous rate of change is we want to find the slope of that tangent. It can be a bit tricky to do, and we'll just kind of walk through it slowly just to make sure we have all the bits and pieces. Let's start, actually, before we get there, again, this kind of summarizes what we just talked about. The instantaneous rate of change is a measure of the rate at a certain point. So the key difference here between the average rate of change and instantaneous is the instantaneous is at a certain point. Now, one of the things that we can do is that we can estimate the instantaneous rate of change by finding the average rate of change for smaller and smaller values of h. So just a reminder that when we looked at the average rate of change, we were finding the slope. I'll use these 2 points again. We were finding the slope of the line that connects 2 points. And we talked about the distance here between the two x values as an h value. And so what we can do here when we want to find the instantaneous rate of change is we just, let's say we wanted to find the instantaneous rate of change right here. What we can do is move h closer to 0. So we can, instead of looking at the distance between these 2 points here, why don't we slide this second point a little bit closer and find this rate right here. And the idea is that by moving that point closer and closer and decreasing the value of h and making it closer and closer to 0, we can get a decent estimate for the slope of the tangent at this point. So the instantaneous rate of change is the slope of the line that just touches the graph. We call that a tangent. And to estimate the instantaneous rate of change, we choose a small value for h. And when I say small, small can be like 0.001. It doesn't have to be that value. Our textbook uses that as their value, so that's a value that we're going to do. Before we do that, though, let's have a look at the graph just to see what's going on here. So we have this curve. This is the graph of y equals x squared. It's in red. And in blue, I've drawn the tangent to that line at this point right here. The tangent to the curve at the point x equals 2. This is at x equals 2. And we want to find the slope of this line. So graphically, it's fairly easy to do. I was able to draw the tangent on there, so the point that just touched the point on the graph, this point right here. So I drew the tangent, and you can do that with a ruler, just moving it nice and close and getting it so that just that one point is on. And now, if we're going to find the instantaneous rate of change, we just need to find the slope of that line. Well, in order to find the slope of the line, we can do that by doing y2 minus y1, sorry, that should be a 1, over x2 minus x1. And another way to think about that, just relating back to what we talked about with the average rate of change, this can be f at x plus h. I'm going to put a little approximate, well, we'll leave it here. F at x plus h minus f at x all over h. And remember, the h comes by doing your x2 minus x1. In fact, I'll put that in here as an intermediate step, pardon me. And so this gives f at x plus h minus f at x. And remember, the difference between those 2 points was h. So this often is called a difference quotient. So I'll just jot that down just so you hear the terminology, difference quotient. All right, so let's go ahead and find the slope of this line. It's the blue line that we're looking at. We need 2 points. Doesn't matter which 2 points they are. So let's choose a couple nice ones to work with. Here's one right here, and here's one right here. So we want to know what's y2, the change in y, or the rise, is here, and the run is here. And you'll see that we went up 4, and we went over 1. So the instantaneous rate of change, so the IRC at x equals 2 is 4. And again, that just tells us how quickly things are changing. If we were to measure the instantaneous rate of change down here at x equals 1, we would see that it's not changing as much. This tangent that I'm sort of scribbling in here is not nearly as steep as the blue line that we have. So it gives us an indication of how steep the curve is at that point. And again, if we wanted to, we'll do an example. In fact, we'll do the same example algebraically. Let's go ahead and do that. Let's do that. Actually, sorry, I'm just going to back up a bit. We'll do that right in here. So we say that the instantaneous rate of change then is approximately equal to the average rate of change. Is approximately equal to the average rate of change, which we said was f at x plus h minus f at x all over h. But we want to choose a small value for h. So we're going to say that h is equal to 0.001. So let's go ahead and figure out the values here. So what we're going to do is we're trying to find the instantaneous rate of change right in here. And we're going to choose an h that's, and I'm kind of blowing this up a little bit here. 0.001 is our distance to our next point. So it's obviously really close, and we're just finding the slope of that line. So f at x plus h is basically going to be, x was 2 here, not 4. So we get 2 plus 0.001 squared. That's our f at x plus h. The function, I didn't write that down here. Oh, the f at x is equal to x squared. So there's our function, our x value plus our h value squared. From that we subtract f at x, which is just x squared. And then we divide by h, which we said was 0.0001. And so we'll just kind of work that out a little bit. 2.001 squared works out to 4.004, and then 2 squared is 4. Again, we're using 2 because we're trying to find the rate of change at x equals 2. And then we're going to divide that by, in fact, maybe I should put the 2 in here. Sorry, I realized I didn't put the 2 in. Then we're going to divide that by 0.001. And when we do that, on the top, we're going to get 0.004 divided by 0.001, which is just equal to 4. You can see we get the same answer here that we had up here. So that means that the slope of, so this instantaneous rate of change tells us that the slope is approximately, the slope of the tangent, pardon me, is approximately equal to 4. And sure enough, we found graphically that it is in fact equal to 4. All right, so now that we've talked about that, let's dig a little bit deeper. This maybe goes a little bit further than we need to go, but we're going to talk a little bit about a limit. So when we were estimating the instantaneous rate of change, we discovered, not by trial and error, but just by looking at it, that our estimate gets better as h gets closer and closer to 0. And that's why we chose h equal to 0.001. In fact, had we chosen h to equal, let's say 0.5, we probably would have found that our estimate wasn't quite exactly equal to the instantaneous rate of change that we got from the graph. So that's an estimate, and the estimate gets better the closer h is to 0. So we actually have in math, we have a term called a limit that gives us a value that we're going to need here. So a limit is a value that a function approaches as the input, or x value, approaches a given value. So the way that we write a limit is it's a little bit weird. I'll do it off on the side here. But here, we could write the limit, so just lim. Now we're going to say that h goes to 0. So this is the limit of the function. We'll talk about this in a second and how it looks in the graph, or sorry, how it looks for the graph that we just talked about. What happens as h gets closer and closer to 0? So what we're trying to do here is we're going to say that the instantaneous rate of change, in the previous example, we estimated the instantaneous rate of change. Now we'll actually calculate it. And again, I'll use the same example so you can see how that works. So the instantaneous rate of change is equal to the limit as h goes to 0. This just means that we want h to get closer and closer to 0. So it's still the same function, that f at x plus h minus f at x, all divided by h. And notice here we've changed from an approximately equal to an equal sign. So that limit is something that we don't really need to explore a whole lot in this course, but I wanted to talk about it because I know some of you might be curious about how do we show that h is going to 0, and this is how we do it right here with this limit as h goes to 0. So I'm going to use the exact same example here. I'm going to find a function now, a function that gives the instantaneous rate of change of this function. So we're finding a function that represents the slope of all of the tangents of this function here. And the nice thing about this is that once we do it, we can find the instantaneous rate of change for any x value. So let's go ahead and find the function. So we know that the instantaneous rate of change is equal to the limit as h goes to 0 of f at x plus h. Oh, I lost my plus h. Let's try that again. Minus f at x all over h. Now, it's really important that we keep this limit as h goes to 0 here because we don't want to change the value of our expression at all. So this is going to be the limit as h goes to 0. And we'll see how it comes into play in a moment. Now, just a reminder, here's our f at x right here. It's x squared. F at x plus h. We did this on the previous page, but it probably doesn't matter. We can do it again. Just means substitute an x plus h into the function everywhere we see an x. So we get this. So our function becomes x plus h squared minus f at x, which was just x squared, and all of that's over h. I'm running out of room here. See if I can squeeze it all in over here. So that instantaneous rate of change is still going to equal the limit as h goes to 0 of, and we're going to expand that. When we expand the binomial, remember it's x plus h times x plus h, which gives us x squared plus 2xh plus h squared. So that part here is just the expansion here. From that, we're going to take away an x squared. So let's go ahead and subtract x squared. And we're going to divide all that by h. And then just like we did with the average rate of change, we can simplify this. Again, let's keep that limit as h goes to 0. You'll see why in a moment. And notice here we can subtract out x squared minus x squared is nothing. And just like we did with the average rate of change, we have an h in both of these terms. So let's go ahead and factor out the h. Again, we just want the h And when we do that, we'll get a 2x here plus an h over here, and all of that gets divided by h. And again, just like we did with an average rate of change, we have an h in the numerator and an h in the denominator. We can divide those out. Now here's where the limit comes in. Notice before, we couldn't set h equal to 0, because if we set h equal to 0 here, we would have a 0 in the denominator. We can't divide by 0, so we would be stuck. So the nice thing is that now our function, our instantaneous rate of change function, looks like this. It looks like the limit as h goes to 0 of 2x plus h. Well, we want h to go to 0, so this is where we substitute a 0 in for h. Now again, we can only do that after we've gotten rid of the h in the denominator. So we're going to substitute h equals 0 into our function right over here for h. Everywhere there's an h, we're going to replace it with a 0. So our instantaneous rate of change then becomes 2x plus 0, which is just equal to 2x. So this function right here represents the instantaneous rate of change function, which means that when we get to part B of this question, we're trying to find the slope of the tangent at x equals 3. This function gives us all of the slopes of the tangents. At x equals 3, that function, the instantaneous rate of change, is equal to 2 times 3, which is the same as 6. So that means that the slope of the tangent at x equals 3 is 6. So that slope of that tangent is equal to 6. So that's an introduction to the instantaneous rate of change. We'll see it a lot for a lot of different functions. I wanted to show you the graph. I wanted to show you how to estimate, and I actually wanted to show you how to calculate the instantaneous rate of change using some limits.